Hello, my name is Evan Septino, and my NIM 221011060010. I will give you an explanation of my paper titled Graph Mining. Introduction. Graph mining, a vital area within data mining and network analysis, focuses on extracting meaningful information from graphs, which are interconnected data structures. In today's world, where complex relationships and interconnected systems are prevalent, graphs provide a versatile framework to represent a variety of phenomena, from social interactions to biological networks and infrastructure systems. Utilizing graph mining techniques, researchers and analysts can uncover hidden structures, linkages, and patterns within these complex networks. This helps with knowledge discovery, innovative thinking, and informed decision-making across different fields. Fundamentally, graph mining involves extracting relevant data from graph-structured data, where nodes represent entities and edges denote connections or interactions between them. This structure captures both the attributes of the nodes and edges, as well as the topology of their connections, providing a comprehensive understanding of interconnected systems. For instance, in social networks, graph mining can reveal information dissemination patterns, community structures, and influential individuals, aiding in targeted marketing, social network analysis, and content recommendation. Pioneers like Jiawei Han, Christos Faloutsos, and Michalis Faloutsos laid the foundation for essential algorithms and approaches in graph mining. Early methods, such as frequent subgraph mining and graph clustering, evolved into advanced techniques like graph neural networks, graph embeddings, and graph convolutional networks, which utilize machine learning and deep learning to model complex graph structures and generate informative representations. Graph mining has numerous applications across various fields, including recommendation systems, bioinformatics, social networks, cybersecurity, and transportation networks. In social networks, it supports viral marketing campaigns, influence propagation analysis, and community detection. In bioinformatics, it aids personalized medicine and drug discovery by analyzing biological networks. In cybersecurity, it facilitates anomaly detection, threat intelligence, and network intrusion detection, providing protection against cyber threats. Literature review. The literature on graph mining is diverse, encompassing seminal works, current studies, and innovative approaches. Initially, graph mining focused on basic methods for identifying graph motifs, extracting frequently occurring subgraphs, and clustering nodes based on structural similarities. Jan and Han's development of GSPAN, a graph-based substructure mining algorithm, was foundational. Borgward and Kriegel's work on graph kernels provided a framework for classifying and comparing graphs based on structural features. Popular methods like graphlet, random walk, and shortest path kernels have applications in cheminformatics, social network analysis, and bioinformatics, where evaluating graph similarity and classification are crucial tasks. The integration of deep learning techniques has revolutionized graph mining. Graph neural networks, GNNs, enable learning useful representations and capturing intricate graph structures. DeepWalk by Perozzi et al. Introduced a method for learning node embeddings using random walks, and skipgram models, paving the way for advancements like GraphSage and Node2-Vec. Graph convolutional networks, GCNs, by Kipf and Welling, allow for convolutional operations on graph-structured data, making tasks like link prediction and node classification feasible. Graph mining research spans various applications, including recommendation systems, social network analysis, biological network analysis, cybersecurity, and transportation networks. Techniques like community detection and influence propagation analysis in social networks support marketing campaigns and user engagement strategies. In bioinformatics, graph mining helps analyze gene regulatory networks and protein-protein interaction networks, advancing personalized medicine and drug discovery. In cybersecurity, graph mining algorithms model network traffic, communication patterns, and system logs as graphs, enabling anomaly detection, threat intelligence, and network intrusion detection. In recommendation systems, graph mining provides personalized recommendations by representing user-item interactions as graphs. In transportation networks, graph mining aids infrastructure planning, traffic prediction, and route optimization. Applications. Graph mining's versatility allows it to be applied in various contexts, revealing hidden patterns, identifying anomalies, and streamlining operations. In social networks, it helps understand social dynamics, identify community structures, and predict user behavior. Social media platforms generate vast amounts of connected data, capturing user interactions and information sharing. Graph mining techniques like community detection algorithms find coherent user groups with shared interests or social connections. Influencer propagation research identifies key users or content, facilitating content recommendation systems, viral marketing strategies, and targeted marketing campaigns. In bioinformatics, graph mining analyzes biological networks, such as metabolic pathways, gene regulatory networks, and protein-protein interaction networks. These networks provide insights into cellular processes, disease mechanisms, and drug-target interactions. Graph mining algorithms identify functional modules, disease-associated genes, and drug candidates, advancing personalized medicine, drug discovery, and precision healthcare. In cybersecurity, graph mining supports threat intelligence, network intrusion detection, and anomaly detection. Analysts use graph-based representations of system logs, network traffic, and communication patterns to detect malicious activities, spot suspicious behavior, and mitigate security threats. Graph mining algorithms identify patterns indicative of cyber attacks, such as botnet activity and network breaches, enabling proactive threat prevention and incident response. In recommendation systems, graph mining enhances user satisfaction and engagement by providing personalized recommendations. Collaborative filtering methods and graph-based representations find similar items or users based on connectivity patterns. Analyzing interaction network topology and using graph-based recommendation algorithms generate precise and engaging recommendations for users. In transportation networks, graph mining aids infrastructure planning, traffic prediction, and route optimization. Complex networks representing road networks, public transportation systems, and traffic flow are analyzed to identify traffic congestion, improve public transportation efficiency, and plan vehicle routes. Utilizing graph-based representations and advanced analytics, transportation planners can make informed decisions to enhance mobility, reduce congestion, and improve overall transportation system efficiency. Discussions. Despite its potential, graph mining faces several challenges and concerns that need to be addressed. These challenges are methodological, technological, and ethical, affecting scalability, interpretability, and ethical implications of graph mining techniques. Scalability is a fundamental issue, especially with the exponential growth of graph datasets across various fields. Traditional graph mining techniques may struggle to handle large-scale graphs effectively, leading to scaling issues and processing bottlenecks. Distributed computing frameworks and scalable algorithms are required to process and analyze large graphs efficiently. Combining distributed and parallel graph processing methods can enhance scalability, enabling real-time or near real-time analysis of massive graphs. Interpretability of complex graph mining models is another challenge, particularly with the use of deep learning methods. Deep learning models, including graph neural networks, GNNs, often exhibit black box behavior, making it difficult to understand the underlying mechanisms behind insights and predictions. Interpretability is crucial in areas like criminal justice, finance, and healthcare, where decisions have significant consequences. Techniques such as explainable AI frameworks, attention mechanisms, and model-agnostic interpretability methods can enhance the interpretability of graph mining models, fostering trust and understanding among stakeholders. Ethical concerns such as bias, fairness, and privacy are also relevant in graph mining. Data security and privacy issues arise as graph mining algorithms may inadvertently expose sensitive information about individuals or groups. Additionally, biases in the underlying data can propagate through graph mining techniques, leading to unfair or biased outcomes. Considering ethical implications and ensuring proper safeguards to protect privacy and fairness are essential. Implementing privacy-preserving approaches, ethical guidelines, and fairness-aware algorithms can help ensure graph mining applications adhere to ethical standards and principles. Methodological factors such as algorithm selection, feature engineering, and representation also impact graph mining. The choice of feature extraction technique and graph representation significantly affects the efficiency and effectiveness of graph mining algorithms. The design and implementation of algorithms must account for specific data characteristics and challenges such as sparsity, heterogeneity, and noise. Evaluating scalability, generality, and resilience of graph mining methods ensures their applicability across diverse datasets and domains. Conclusion: graph mining stands at the forefront of data-driven research and practice, offering a powerful toolkit for gaining valuable insights from interconnected data structures. By exploring graph representations, algorithms, and techniques, researchers and practitioners have opened new avenues for knowledge discovery, decision-making, and innovation in various fields. This work provides a comprehensive examination of graph mining, covering its theoretical foundations, methodological approaches, real-world applications, and future directions. Graph mining has evolved significantly, driven by advancements in computational techniques, data availability, and interdisciplinary collaboration. From its early roots in basic algorithms for frequent subgraph mining, it has transformed into modern, deep learning-based graph representation learning. Graph mining is crucial for revealing hidden structures, linkages, and patterns in complex networks, with significant implications for innovation, knowledge discovery, and decision-making. In fields like social networks, bioinformatics, cybersecurity, recommendation systems, and transportation networks, graph mining techniques enable targeted marketing campaigns, personalized treatment, threat detection, recommendation systems, and infrastructure planning. However, graph mining also presents challenges and concerns that need to be addressed. Scalability, interpretability, methodological challenges, and ethical implications hinder the widespread adoption and deployment of graph mining techniques. Ensuring that graph mining applications respect privacy rights, adhere to ethical norms, and eliminate biases requires interdisciplinary collaboration, methodological advancements, and ethical principles. The future of graph mining is promising, with potential for significant impact and innovation. Emerging trends such as federated learning techniques, exploiting heterogeneous information networks, and integrating temporal dynamics into graph analysis present exciting opportunities to advance the field. Interdisciplinary collaboration and ethical research practices are essential to overcome challenges and fully realize the potential of graph mining to address complex problems and achieve positive social impact. In summary, graph mining offers significant implications for knowledge discovery, innovation, and decision-making. By embracing challenges, seizing opportunities, and fostering ethical research practices, we can unlock the full potential of graph mining to address complex issues and enhance society.